all aware, our test 2 is Thursday, right?
What? No.
And again, you can bring one sheet of notes, write anything you want on both sides. You might bring your book for the tables, because some of the problems will require you to use the F table or the whatever, T table or something. So bring your book for tables. Okay. Well, this handout that I've just given out today is our last major topic, repeated measurement designs. And so we'll spend 3 days or something like that talking about this. And then there's still a few more days of class left. I'll try to figure out something to talk about for those last few days. We'll see. So the basic idea with repeated measurement designs is that we're going to have some kind of subjects that we're going to repeatedly measure. So people might take a series of tests, or a company might be measuring its sales January, February, March, April through a series of months, so that we get several measurements on the same unit. So this is a layout of the simplest repeated measurement designs. So over here on the left, I list subjects 1 through S. And then for the columns of this array, that will be the factor. We have one factor that we're going to study. That will be the factor that we're interested in. So there will be A1, A2, A3, up through A whatever up there labeling the columns. So in general, we're going to have data that will be indexed by 2 subscripts, I for the subject and J for the treatment. So here's a typical model for this kind of problem. It's the simplest model that we've encountered for a while. Yij is some constant mu plus a subject effect plus a treatment effect plus a random error. The treatment effects are assumed to be fixed. So notice this is the typical condition for fixed effects on the factor B. Well, it's called A. This is not good notation. Probably I should have called that factor B. Anyway, it's factor A. And the sum of those coefficients is 0. The subject effects, rho I, are random. Normal 0, sigma squared rho. The errors, as typical, are normal 0, sigma squared. So here we have a model where the subjects are random, the treatment is fixed, and let's see what that will do. Primarily, we would be interested in assessing the treatment effects. Are there any differences in the treatments? If so, how much? And so on and so forth. So here's the first example which I took out of our textbook, 27.3. What is that again? I kind of forget. 27.3. Yes, when you look, you can see that chapter 27 is about repeated measures and related designs. And so on the first page, you see a model here which looks just like the model on my handout. So that's on page 283. Here's the assumptions that are typical. This layout at the bottom of the page reminds us of something. The treatments don't have to be all in the same order. So for the first subject, the order is T4, T3, T2, T1. For the second subject, it's a different order of treatments. So we generally randomize the order of the treatments. Now 27.3 must be one of the exercises. Let's jump ahead here. See if I can find it. There. Relationship between the dose of the drug and the increase in blood pressure for laboratory rabbits. So it's the 12 rabbits received in random order 6 different dose levels of the drug with a suitable interval between each drug administration. The increase in blood pressure was used as a response variable. So here's the data. You can see that there's 6 rabbits, then 12 rabbits were used in the experiment. So the rabbits are the subjects. And then the treatment is the dosage of this drug. And here's the dosages arranged in an increasing order. But again, remember that the actual administration of the doses would be some random mixture of those 6 choices. So this is the data anyway that we're dealing with in example 1. Blood pressure of rabbits. So actually, if you want to turn the page, the actual data is there on the second page, printed out. So the subject goes 1 to 12, and there's 2, 4, 6 observations for each subject, and the treatment is factor A, and there's 6 levels for factor A, you see here, and then the Y column is the actual data. So this is the data that I have in the Minitab columns to get this working. So as you've seen me do before, I'm instead of typing these numbers in directly, I'm using the Minitab set command to set up some of these columns of solid numbers. Set C1, 1:12 in parentheses 6 times. So that generated first column over here. So when the constant is at the end of the parentheses, this is the way it's interpreted. And in the next case, set C2, or 12 parentheses 1:6. When the constant 12 is in front of the parentheses, it generates second column here. So this is standard Minitab syntax for the set command. It's convenient to use instead of typing in all the numbers. So anyway, we have those being set up, and then I use next in Minitab, as you see here, the ANOVA command. I'm not sure why I switched from GLM. That would have worked just as well, probably identically as this did. But anyway, I've used the ANOVA command here on this. Example. So notice our model is simple. We have y equals subject and then A. And then in the subcommand, I specified that subject is going to be random, typically in repeated measurements designs. That's almost always going to be the case because the subjects are selected from some bigger population of available subjects. So here they're the rabbits. Okay, so here's the standard Minitab output. Here's the ANOVA table right here. And this isn't very interesting because the F statistics are so big, the p-values are so small, essentially 0, so we're going to be rejecting H naught about no A effect. We're going to be rejecting H naught about no subject effect. So that's kind of obvious when you look at the ANOVA table, what conclusions we should make. The expected mean square information tells us that 3, the error mean square, should be the denominator for both of the other 2 tests. And that would be checked out by looking at the previous ANOVA table. Here's some descriptive statistics about factor A, in particular, here's their means. There's the mean. So if you turn to the third page then, to explain a little more what's happening here, here's a plot of response Y against factor A. And factor A had 6 different dose levels, 1, 2, 3, 4, 5, 6. And you notice there's an obvious effect in factor A. As the dosage level increases, the response Y also goes up. There it is. So that graph explains why there's a factor A effect. Then here's the plot of the Y against the 12 subjects. And this is much more scattered and jagged, of course. But remember, the test of the hypothesis said to reject H naught, conclude there's differences between the subjects. Well, it's hard to see where the differences are, but there are apparently enough differences here to enable us to reach that conclusion. Okay, so that's the first example, a simple example about a repeated measurement design. Here's another example, and I think there's enough description here for you to get the idea as to what this experiment was all about. Fabric for athletic gear was tested by measuring evaporative water loss. So 5 test fabrics were used. So we have 5 different shirts or something like that to be worn by athletes or by exercisers, joggers, whatever they're doing. And somehow there's an instrumentation that can measure how much water is evaporating from the fabrics. 5 subjects took part in the experiment. So this is kind of a small-sized study, which is 5 subjects. So here's a layout of the data. The subjects over here on the left, 1 through 5, and in the columns I've labeled by the 5 different types of fabrics, 1 through 5 again. And here's the response, this evaporating water loss. So what I have to do now is to get this data set up so I can run Minitab. And so I'm going to use the stack command here. Basically what I'm going to do is to say, well, I typed in these columns in Minitab. So now what I needed to do was to get these responses arranged in a single column. So here I stacked C2 through C6 and put it in a new column C7. So that's going to arrange these in a single column C7. Then I'm going to set a new column C8 to be 5 to 5. And then I'm going to set another column C9 to be 1 through 5 parentheses 5. And so, like in the previous example, I'm setting up these indicator numbers for subject indicator and then fabric indicator. So that's what's going on here. Now, when I was in Minitab, after I had set up these columns, I typed in at the top the names that I wanted for these columns. So the names are going to appear in the output rather than in this business of C7, C8, and C9. So that's good. That happened. But before I did that, I named these columns Fab 1, Fab 2, Fab 3, Fab 4, Fab 5. And so this command here says to Minitab, give me the covariance matrix of those 5 variables. And so what comes out here is the variance covariance matrix for these 5 variables. Now what this matrix has is down the diagonal, it has the variances of the 5 variables. And in the off diagonal spots, it has the covariances. And so that's what you see here. This is actually supposed to be a full matrix, but since it's symmetric, the upper portion is the mirror image of the lower portion. Minitab only printed out the lower portion. So there's a number here, which would be this minus 1.24. There would be a number there, which would be the next number in this, and so forth and so on. So anyway, here's the variance covariance matrix of the 5 variables in this experiment. Now, the textbook talks about this more. I don't have comments about this in my handout. But basically it says with this model, the variances of the y's should be equal, and the covariances between any 2 responses should also be equal. So we look at this result, and we're looking at these variances down the diagonal, and we say, those don't look very equal. So we seem to be violating the assumption of equal variances. Then we look at the off-diagonal entries, the covariances. Theoretically, in the model, these are all supposed to be equal. Well, with actual data, they're never going to be perfectly equal, right? There's always going to be some variation. But you look at the values for these covariances over here, and they're quite varied in their values. So I wrote over here just a little comment. This is not good. This is indicating that the model that we're trying to use perhaps isn't a good choice for this data. But having made that observation, we go on and analyze the data anyway. So that's right here with the ANOVA command. The loss in water equals subject fabric, random subject, and the rest of this is just boilerplate. So here's the ANOVA table. Where am I at? Okay. Here's the ANOVA table, and again, it's obvious how to interpret it. We look at the 2 p-values. The first one is bigger than 0.5, so we accept H0, no subject differences. The second one on the fabric is less than 0.5, so we reject that H0 and conclude there is a difference in these fabrics. So that's how we produce the ANOVA table. Then I have these means printed out at the end, and we could do something with these means. For example, if we wanted to do pairwise comparisons here on the fabric variable, we could perhaps try tricky pairwise comparisons. We would say we take the difference between 2 means, plus or minus a 2 factor times a standard error of the difference. And the standard error for the difference is going to be something like 1 over sample size is 5 plus another 1 over 5 times the estimate of sigma squared, which in this problem is the mean square error. And that's visible even up there at the top of the page where it said that the denominator for testing fabric was 3, namely the error. So I guess this is the mean square error right there, 14.176. So we'll slide that out. Like that. And that's the variance, so we have to have a square root to get a standard deviation. And so that's that piece. Then we'd have to get the piece from the TUI cable, and that would be called what? Q, let's say we want 0.95 for the confidence. We have 1, 2, 3, 4, 5 groups, and the degrees of freedom for the error is, let's go back and look it up. 16. Notes, let me try to look that number up. Let's do nice range distribution, 85% would be this page. And we have 5 groups, and what was it again, 16 degrees of freedom. So I'm reading off the table here, 4.33. I didn't bring a calculator with me to class today. Somebody take out your calculator and work all this out. 4.33 times the square root stuff here. What do we get?
You need to divide that by the square root of 2.
Pardon? Oh yeah, you're right. This should be right here.
7.29.
The whole thing?
Yeah.
So any two means that differ by more than 7.29 are significantly different. Well, this 12 is obviously going to be different than the first one. The second one, yeah. And no, it's not different from the other two. So if I try to arrange these in an underlying fashion, I would start with group 1, then group 3, then group 4, then group 5, then group 2. So there's the groups arranged in increasing value of the mean. Now let's see which ones are equal. 1 equals 3, yes. 3 equals 4, yes. 4 equals 5, yes. 5 equals 2, yes. Okay. So now we times 2. I didn't do that the way I wanted to do it. 1 equals 3. Yes. Now 1 equals 4 is what I should have done. Yes. 1 equals 5. I'm close. That is a yes. And then 1 versus 2, I don't know. So I stop there. So we go 3, 4. 3 equals 4. Yes. Then 3 equals 5. Yes. Then 3 equals 2. No. So I stop there. So that line is redundant because it's contained in the first line. I could omit that one. But that's
Right.
So we'll start at 4. 4 equals 5. Yeah. 4 equals 2. Yes. And then we have, lastly, 5 against 2. So 9 against 12. Is it equal? So this one is redundant. I should erase it. But the other 3 lines are different and contain different information. Well, wait. This last one is also redundant, isn't it? So I guess we could omit both of those as being redundant. Where am I at there? So anyway, since we have concluded that there is a difference due to the fabrics, pardon this here. We should do some kind of follow-up confidence intervals to check out which fabrics are different from which other fabrics. And this is one approach to use Tukey's simultaneous confidence intervals. Okay, now we have a new kind of example coming up here. It's called here a two-factor problem. So basically in the previous examples we've had subjects measured on one factor over time. Now we've got two factors. So notice the way this is laid out. We've got factors A and B. Factor A is sort of like a blocking factor really. A is 1, we've got a bunch of subjects, and we measure B. A equals 2, we've got a bunch of subjects, we measure B. And so forth through some ending point on factor A equal little a. Now, these subjects are all distinct, so we have, in this example, we have A times S subjects. So we're using different subjects in the different levels of factor A. Now we need a model for this two-factor problem, and that's given down here. Now notice what's happening here in that we have an overall mean mu Now, I guess A corresponds to I. No, A corresponds to J. Subjects corresponds to I. And then B corresponds to K. So we have row I nested in J. So what that's saying is that subjects are nested in factor A. And if you look at the situation, they are, right? That's what we mean by nesting. So subjects are nested in factor A, and we indicate that in our model right there with that nested parameter. Then we have an A effect, alpha J, for differing A effects. Then we have a B effect, beta K, and then we're going to allow interaction between A and B with an interaction term, alpha, beta, JK. So these are the terms that we want in our model. And the thing that's different to notice is this nested term right here. And this kind of layout has subjects nested in factor A. Subjects are not nested in the other factor B. So here's an example. Let's see if I can describe a little more detail about this example. Basically, we have 12 subjects, which are people, and we want to study the effects of 3 different kinds of food on their glucose levels. So we have a column for diet, diet 1, diet 2, diet 3. And then we have a column for subject. Now, even though these are 1 through 4, 1 through 4, 1 through 4, there are 12 subjects overall in this experiment. So notation isn't really good in that sense. There's 12 different subjects in this experiment. So factor A is the diet. There's subject. And now factor B is this time business up on top here. We're going to measure the glucose levels after a certain number of minutes. After 15 minutes, after 30 minutes, and after 45 minutes. Now this is again a repeated measurement experiment because we're getting multiple measures on the same person. So for this subject, we get 3 measurements. For this subject, we get 3 measurements, and so forth down the line. So we have a repeated measurement scenario here. With factor A over here on the side, the diet, factor B on top, the time waiting in minutes. Okay. These numbers, these responses in a single column, for example, like I did in the previous example, but I didn't show you any of the lines that I did in main tab at this point. I went directly to the ANOVA command. So the glucose column is a column of the responses arranged in a single column. Then we have diet, which is the column of the diets suitably expanded. Then we have subjects, parenthesis diet, to indicate the nesting that's going on here. Then we have time, the B variable on top, and then the interaction diet by time. So there's a typical Minitab command line to fit our model. Random subject, that's okay. And the rest of it is kind of boilerplate. So we look at the ANOVA table that appears here, and it's either exciting or boring, depending on how you look at this. all the p-values are very small, we would reject all the hypotheses, right? So we would say there's a difference due to diet, there's a difference due to subjects nested in diet, there's a difference due to time, and there's an interaction between diet and time. One thing that's different in this little table that you can spot down here in the expected mean square column is right there. We're testing about the first variable. What is it again? We're testing about the first variable, diet. The proper denominator is 2 in this nested sum, mean square. You can see that over here in these numbers. If you want to test about the first factor, there it is. You have to find the denominator, whose expected value will be 5 plus 3 times 2. So there it is coming up right next. So we just read it right off and say, that's the proper denominator for testing the first variable. For all the others, possible denominator is simply 5. And so that's what we can do.
So for our NOVA table, it has significant interaction. We can still say something about the main effects.
Well, we run into that same old problem again, right there. We have interaction. And so if we want to say there's significant main effects, maybe we should hold back, say that very softly. And I would say what should be done would be to explore some graphs, to draw some graphs of the interaction to see what makes sense. It could be that the interaction is mild, and then we'll ignore the thought you raised. Or it could be that there's a decent amount of interaction shown in the plot, and then we wouldn't really want to go on and state those conclusions about the main effects. So it's that age-old problem again that we encounter when we have more than one factor in ANOVAs. All right, so on the next page are the means, but more importantly, here's the plot. So here's the plot of response versus diet. And so you can see there's a definite effect there. And the second plot is the response versus time. And that doesn't look quite so dramatic, but yet apparently it's statistically significant. Now what I don't have here for the question that you've raised is the interaction plot. And that's the one that I should have here to respect this issue. So they put a little note along the side here, better to get an interaction plot between the factors diet and time. Okay, so at the bottom of page 7, it says an important situation. And it's followed with an example of this important situation. Now, I think this is the point where I'd like to stop for today. Let's have a shorter class today. You've got some other things to do, getting ready for our next class, right? So let's just stop class a little short today, and we'll pick up this topic after the test and talk about it in school. Okay?